What I will speak for a while will have nothing to do with, apparently, with multi-zeta value. The relation is that we thought some expression for multi-zeta value as iterated integral, and now the natural home for iterated integral is Chen's theory of iterated integral related to the fundamental group made unipotent. So first I will explain the story of part one of first general group made unipotent, and I will try to explain it from different point of view. So I hope you will not be as angry as my children were. They've been coming home from school and I was giving 5 ways of looking at the problem they had in school, and they just wanted the solution. And in fact, I don't think I can go up to 5 for this, but so let pi be some finitely generated group. And I will consider coefficient of pi for the central descending series. And so this is, this is nilpotent. How does one say for group? Nilpotent group. And as such, is torsion subgroup, but a torsion element from invariant subgroup, and I have nothing to tell about them, so I divide by this torsion subgroup also, and let me call this gamma. So if I have such a group, so I have gamma, I can look at gamma modulo its commutator, and I also divide it by its torsion. So I have the following chain of group. I have gamma, which is Z1 of gamma. I have Z1 of gamma, but I make it slightly bigger. If there are intercoefficient some torsion element, I put that into Z1. So to that, then I have Z2 of gamma, but also if there are some torsion element in gamma modulo Z2, I add them to Z2 and so on. So if I look at the successive coefficient, I have here some free abelian group, another one, and so on, until I stop at Z n plus 1 gamma. So here I have some coefficient Z. Sorry, I got my index. Gamma is equal to Z1 of gamma, so I should have. So I have this composition theory, and successive coefficients are just free abelian group. So I start with pi. That's what I want to do. It will be some fundamental group. But immediately I replace it by some coefficient for the central descending series. Eventually I will take the projective limit on n. But for a while I consider just this coefficient, pi modulo nth term of the central descending series, and I use this finite composition series with successive coefficient being free. Yes, except I stop somewhere. I stop at this stage. Yes. So one can use this picture to find some kind of coordinate on gamma. So let me choose basis E1 up to N1 here. Same there, and also let me lift those bases into corresponding group. So I have a series of elements of gamma, which I will call E11 up to En11. So those map to a basis of gamma made abelian modulo its torsion. then for the next stage, I have E2, 1 up to E2 and 2, and so on. So those are all elements in gamma now. Now, if I look at them as an ordered system of elements of my group. Now, if I take any element of my group, first I can consider some product of the EI at correct powers, so that I get my element intercoven, in this coven Zn1. And then I have my original gamma is such a monomial in those elements times something which is in the next subgroup, and so on. So any element gamma can be uniquely written as E11 at some power n11, and so on, up to E n and n at the power n and n. Sorry for. So I have a coordinate system. I have a bijection between gamma and z at some big power. Now, what good is it? What one check? Now, one has a coordinate system for the group, and one can try to write the multiplication law in those coordinates. And the result is that the product law is given by polynomial formulae. There is a twist. So it's polynomial with rational coefficient, of course in two a variable for gamma 1, or the a variable for gamma 2, and I want the coordinate of the product. But of course, I want this to be gamma times gamma 2 gamma, so I want integral value. Now, when one has such polynomial formula to describe a group law, I can forget that my coordinates were integers, and I can take them rational number. Yes, I have rational coefficient, so I would be a little troubled to take in any ring as coefficient, but I can take Q coefficient if I want. Now, if one take Q at the power A, with the multiplication law, the group law given by the same formula, that's what one calls Maltsev completion of gamma, and it somewhat could be called gamma tensor Q if one wanted. But more important for me is that I have really polynomial formula, so I have an algebraic group. Over Q. And something else which one has is I had some freedom in what I was doing here. I can change another system of base and of lifting of the bases, so another way of parameterizing my group by a-tuples of integers. And then I have a change of coordinate formula, and also the change of coordinate will be given by polynomial formulae with rational coefficient and integral values. One also understands somewhat what kind of denominator one has. The only denominator are those involving prime up to n. And the case of, if n is prime, the case of n is somewhat borderline. What happens is that if I choose such a basis, I have polynomial formulae for the group law, and L will not occur in denominator, this least one, L equals n. But what will happen is that if you look at the change of coordinate formula, then you will have L. Maybe it's easy to see what happens on an example. So I consider the group generated by element x and y. Also, there is a central element C. And the law is that y, the relation is that C is central and yx equals C xy. Now, an element of this group can be uniquely written as x to the power p, y to the power q, c to the power r, and it's easy to see that the group law will be given by p, q, r, p prime, q prime, r primes equals p plus q, p prime, q plus q prime. This is not surprising. If I kill the center, I obtain just z2. This is what I see here. Also, I want to have r plus r prime, but also I will have plus qp prime. So here I remain with integral coefficient. But now, if I want to change coordinate, I would like, for instance, to use rather the element x, xy, and c, and to see what happens there, and how to change from the system of coordinates attached to this system of elements to this one. So what this implies basically is computing xy at some integral power n and expressing it in the previous format, in this format. Now you see you have xy, 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 xy n times, and you want to have the x jumping over the y's, to have all x first, then all y's, and then you have some central element which will occur. So you have to count how many jumps you need for a x jumping over a y when you do this, and you will find that it is n minus 1 over 2, and that's the denominator which occurs in this. And that continues for more complicated group. So you still, when you have just two levels, find some algebraic group over Z, but they are not canonically attached. And the deeper you go, the more trouble you have with denominators. Yes, now I will make some transition to some other point of view. What's the meaning of those integral value function on the group which we obtain by writing uniquely an element of the group in this form? I have all those functions, and what are their properties? And one has, say, let me tell over Q first. Yes, so the function on the group are, you have a polynomial algebra with as many generators as you have elements on those bases altogether with some law, and the functions are just the polynomials in those exponents which did occur. And now on this affine algebra of the group, one has a natural filtration occurring. First you have all the n1s, which are just linear coordinate on the group made abelian. Then you can look at product of two n1s, and also you take n2. Then you take product of 3, when you want a filtration of algebra. So, and at each stage you add the coefficient will occur for the corresponding level. So you have a natural filtration on this algebra, and one can kind of understand what those successive pieces mean. Let me just tell it first in the simplest case where I just take the group Z. So now I am telling that the affine algebra I want to consider is the algebra of polynomials, integral, or really what I wanted first were polynomial with rational coefficient and integral value. And I have here the filtration I get is simply the filtration by the degree of this polynomial. So I want to tensor everything with Q first, otherwise I will be in trouble. So if I look at one coordinate system, I have coordinates coming by bunch. And the filtration is a filtration of algebra. I first put the first bunch. Then I put the first bunch or product of element in the first bunch and the second bunch. And then each time I add the next bunch of coordinates, but as I want a filtration of algebra, I want fi times fj containing fi plus z, so I am forced to add product of things which came before.
So the algebra that you are considering right now is the enveloping algebra?
No, I have no Lie algebra so far. It's the affine algebra, so I have defined this group gamma unipotent. It has an affine algebra, which is the algebra over Q generated by indeterminates corresponding to those bases. And essentially what I am telling is that I consider those as to being of degree 1, those of degree 2, then of degree 3, and so on. And I look at all monomial of degree at most something. And this gives me a filtration. There will be no grading by degree in general for a general group, but the filtration makes good sense. And if I take the special case of the group Z, I get the polynomial in one variable and the filtration by degree, because I am just telling that in filtration 1 I want to put the indeterminate t, and then I am forced to add. Now, a polynomial of degree at most d is characterized by the property that if you take which one? So constant, it's d1. If you take a d plus 1 difference, you obtain 0. So for instance, if you have fn plus 1 minus fn equals 0, this is the first difference. This implies you have a constant when you have a polynomial. So that is mean degree at most d. And we have something a little more general to characterize. You can look at f. You can, instead of just 1 as difference, you can take number a1 up to a d plus 1, and then consider all the following expression: f of n plus summation of ai for I in some subset of 1 to d plus 1, with a sign minus 1 at c power the number of elements of I. So for instance, for 2 elements, you would look at f of n plus a plus b minus f of n plus a minus f of n plus b plus f of n. And if this is 0, this means that you have a linear function. And it's enough to ask it for a equals b equals 1, which was what I was telling Sir. if I have a function either on the line on the integer, delta f is f x plus 1 minus f of x. This is an operation function to function, which I can iterate, so I would better put in exponent.
One variable?
No, I am in one variable. Yeah, I was just looking at z. So just in the case of the group Z, the simplest possible case, one has this interpretation of this filtration, which is filtration by degree here, in terms of iterated difference. And in general, one has a similar interpretation for the filtration which I have told. Z is gamma. So that's the example in this case. And now I want to consider the general case where I have also an affine algebra which is generated as a polynomial algebra by the n something, and it's filtered polynomial algebra. And what is the meaning of being in some particular level of the filtration? What one sees that one has a similar interpretation. So I am considering function of an element of the group. If I give myself element gamma 1 up to gamma d plus 1 in the group, which will play the role of those constants, I will decide to always put gammas and gamma 1 up to gamma d in this order. Then I can also consider f of gamma composed with product of gamma I into some subset of the set of all those gammas, put a sign, and sum. So this is the analog of such iterated difference operator on this non-commutative group. So for instance, for gamma and gamma 1, gamma 2, I would have to consider f gamma minus f gamma 1 minus f gamma 2 plus f gamma 1 gamma 2. And now again, if this is identically 0 for any choice of those gammas, it means that f is in some level of the filtration. And then there is
The gammas, there are arbitrary elements?
yes. I guess one could take only a few of them, but
And your n is characterized, so another way of saying it is like you're taking the dual basis of the basis of z to the a up there to which you
yes, those are yes, the n's are the coordinate in z of a, but
and then you chose a
but when one change of basis, the first one are transformed linearly into the other, but the second bunch one can add some quadratic expression in the first one, and so on. So only the filtration makes good sense.
It's the same as just saying that f, if you extend it to the group algebra.
Yes, that's what I was going to tell. Yes. Yes, the slick way that Ein is telling, which is the one used by Quillen, also is to tell the following. You consider the group algebra of the group, and in it you have the augmentation ideal, so formal linear combination of elements with coefficient 0 at the origin. And Now a function on gamma is a linear form, an element of the dual of the gamma, and so it makes sense to wonder whether some function on gamma vanishes on some power of the augmentation ideal, and you see just by trivial translation that this condition means that the corresponding linear form on Z of gamma vanishes on some power of the augmentation ideal, because this you rewrite essentially as f of gamma times 1 minus gamma 1, 1 minus gamma 2 up to 1 minus gamma d plus 1. So that's the auto-interpretation that to construct this unipotent completion of gamma, you can take the group algebra, you divide by bigger and bigger power of the augmentation ideal. You take, this is a projective system, you take the dual, this is an inductive system, and you take the inductive limit. So this is the construction which you will find, for instance, in Quillen for those unipotent envelopes.
These are the functions on
Sorry?
these are the functions on gamma.
No, linear form. Yes, a linear form on Z of gamma, that's the same as a function on gamma.
Right.
Gamma unit is spec of this.
Yeah, it's just.
Oh,
Yeah, that's right.
sorry. Yes, because gamma is a group, this Z of gamma is B algebra. When you do this in dualize, you still get a B algebra and it's commutative. So that's the spectrum is some scheme, and the coproduct gives the group law, which reflects the group law of gamma. So that's two. One has this picture in terms of coordinate, which for me is mainly useful because it tells quite concretely which prime you have to be wary about. While this picture is kind of much cleaner, and also you can apply it directly to the group pi, and then what you get for each finite level, you can take this pi modulo level of the central descending series. You get a sequence of unipotent algebraic group, and doing this, you directly obtain the projective limit of those unipotent algebraic groups, so it's a group scheme. Yes, if I stop at a finite level, so if I have a gamma which is unipotent of some level, one can also recover the algebraic group over Z with a few prime invert. You look at some level here, and you take the subalgebra generated by that. And this, if you tensor with the relevant primes, you will get an algebraic group, not over Q, but something better. So that's second picture. I still want to give a third one. So to gamma, I want to attach some algebraic group, which will be a unipotent algebraic group. It's clear on the construction, at least the first one, that it's an iterated extension of vector group. Now, I can want to use the Tannian philosophy that to give a group is essentially giving its category of representation. So the representation of gamma un will be, in fact, some representation, some linear representation of gamma, and one has to tell which. Now, if I have a unipotent group, so iterated extension of GA, any representation is iterated extension of the trivial representation. So the representation of gamma I want are the iterated extension of trivial representation, and the converse is quite clear. So the story is that gamma in corresponds to the category of representation of gamma which are unipotent, meaning iterated extension of the trivial representation. Okay, now what we will be interested in is essentially some power 1 made unipotent, and I should explain why unipotent is particularly interesting. You could think of other reasonable things a priori. For instance, instead of taking the unipotent representation, you could take all representation, and then this would give you the algebraic envelope of gamma. So in what sense is gamma unipotent something special, more interesting than the algebraic envelope? The main difference is that if you go from a field K to a bigger field, let me think both algebraically closed, for instance. If you consider the case of gamma unipotent, so if you consider unipotent representation of the group either on a K vector space or a K prime vector space, in the unipotent case, by construction, you have the same irreducible representation, the trivial ones, and everything is built out of it. The X group are obtained the one from the other by extension of scalar, and in some technical sense, the category you have here, you extend scalar from K to K prime, and you obtain the category for K prime. And that's completely false if you consider K algebraic. Already, if you consider a group like Z, and you are considered a K or K prime representation, always K algebraically closed, the irreducible representation are parameterized by the element of K, just one-dimensional multiplying by alpha. Here you have all elements of K prime. So you see you have many more simple representation over K primes and over K. So the group changes. The category of representation, you cannot recover what you have for a bigger field out of what you have for a smaller field. So that's why algebraic is not very useful. You still can do something intermediate which is usefully in some cases. You can give yourself a few, or as many as you want, simple irreducible representation of gamma over the field K, and decide that you only want to consider those representations. Sorry, I want stable by tensor product. So I could take those representations and anything which I have a simple factor of a tensor product of them. And then I can look at all representations which have only those as in a composition series. So iterated extension of pieces of tensor power product dual of something given. And if you do that, it again will be all right to go to some extension of the field.
Oh, I'm sorry. I might be confusing something very elementary, but the K and K prime here are the coefficients right now.
Yes.
So then the K unipotent completion of Z is GA of K, right?
No. No, so yes, VA, yes, the unipotent is just
Unipotent,
VA.
that's right, so-
Yes.
Oh, I see. No, I see.
But
You-
the algebraic
yeah,
one, I have a
yeah,
big
I got,
torus.
yeah, no, I see what you
Yes, and not
No,
VA
it's-
also.
right.
Yeah, so that's the difference between
That was your
to-
point.
now there is this middle ground which can be very interesting. We will meet it at only one case. I will want to consider power 1 of projective line minus 0, 1, infinity. And this maps to power 1 of Gm, which is Z. And I can consider as representation, I can fix an integer n and consider the representation of order n, where Z, the generator of Z acts by a nth root of unity. So the group I get will be an extension of a Z mod n corresponding to the covering, finite covering when I extract the nth root of Z, by the power 1 unipotent for this covering, which is the projective line minus 0, infinity, and all the nth root of unity. So this will occur for the multi-zeta value when the z's are nth root of unity. So this is a case where this middle ground is useful, but case when one has SL2 or GL2 are more interesting.
Is it necessary to restrict to 0 ground fields and all of this?
Yes, because the definition of unipotent, at least I guess you get some pathological object. You could still apply this construction, but what you get is, let it take just a group Z simply. You can still do this, take the group algebra of Z dividing by power of the ideal dualizing, but the algebra you get is the algebra of, I guess, all polynomial with integral values at integers with rational coefficient. I think it's that, I should check. But then you have some group scheme which characteristic 0 is GA, but which become very disconnected in any finite characteristic. And I don't like those animals, but so I prefer to eta b over q or to invert a few primes if I stop somewhere in my descending series. Now, this is some kind of abstract reason about unipotent. There is not a reason why power 1 unipotent, for if I consider the case of an algebraic variety, is a natural object to consider. Now I would have a base bond, because here the base bond is something with arithmetic significance, so I would not forget it. Now the point is that this power 1 made unipotent is essentially controlled by cohomology. And this is not completely true, but what is for instance completely true is that if you have a nice model for the cohomology in terms of differential graded algebra, commutative differential graded algebra, and here it's not just cohomology, but at this, and also same for the point, and the restriction map corresponding to the base point. So if I have an understanding of cohomology at the level of Kotzé, in this sense, some complex with multiplication with a product which gives the cohomology plus this for the base point, then one recover this power 1 made unipotent. But in fact, Sullivan says that this essentially controls the rational homotopy type, and power 1 unipotent is part of this rational homotopy type. Now I want to, now because it's controlled by cohomology, one expects that many things which one can do for cohomology can be done also for power 1 made unipotent. Like for cohomology of algebraic variety, one has Alto's realization, Eladig, de Ram-Betty. So we want the same story here. What this really means is that I have some affine algebra of this power 1 made unipotent. In the petty picture I was using so far, this is the group algebra modulo power of augmentation ideal dualized, limit of those. I have this filtration, and those objects should behave like cohomology group of algebraic varieties. Now I will explain this in two pictures of this. The first picture is the picture of iterated integral. And before doing that, here I was speaking of power 1 because this is little simpler as words, but really it's important not only to have power 1, but also pass from a point to another. So one has, for any base point, one has a power 1, and then one has principal homogeneous space right and left for both when one takes paths for a point to another. And this construction of power 1 made unipotent automatically gives something similar for paths from one point to another. And it's easier to make the drawing for paths, so that's why I tell it here. So suppose you look from paths from one point to another. Now this gives you in particular a chain, and the boundary of this chain is extremity minus origin. So this gives you a map from paths to some relative homology group, relative modulo those 2 points, but you tell what the boundary should be. That's not much. It's just I am first telling that power 1 maps to homology. But now you can do better. If you have the interval 0, 1, you can also look at 0, 1 times 0, 1, and there you have this triangle. So now if you have a path which is a map from 0, 1 to your space, for free you get a map from the triangle to the product of the space with itself, and so you have some kind of triangle in the space, and this is mapped on the diagonal. This is mapped to at x times 0, 0 times 1, I don't know, and this is also projecting to a point. I have those two mapped to x. So in this way, to a path, one attaches this relative cycle, and now this detects more. It will detect what the path is in gamma modulo the next level of the central descending series. And now you can continue. This was, you have a simplex in 3 dimensions and so on. And so you have a whole, to a path, you attach a whole sequence of relative chain, which have some compatibility between them also. And in this way, you detect homotopy made unipotent. It's only modulo unipotent that this gives something useful in terms of cohomology of power of the space, relative cohomology. So that's one way to see how homotopy is controlled, by one is omnipotent, is controlled by cohomology. There is another way which is useful also, even if a little more vague. It is to try to see how the cohomology controls the category of unipotent representation of pi 1. So, first stage, you have the trivial representation. Next, you would like to understand the extension of the trivial representation by itself. Now, those are classified by h1 of x, so that's a good start already. Now, suppose that you want to have an iterated three-step representation, and you can give yourself the extension class here, the extension class here, and you wonder if you can fit it all together in something three-step, and in how many ways. Now, so you have those two extension class which give you two elements in H1. You have an obstruction which is the cup product of A and B in H2 to be able to have a triple extension. And if the obstruction vanishes, you have some freedom. You can essentially, to one solution of the problem, add an extension of top by bottom. Now, this looks a little awkward essentially because I have used just a cohomology group instead of using something like the Ham complex or the algebra which computes the cohomology. Because if one thinks in terms of a differential graded algebra controlling, giving rise to the cohomology, then the picture becomes more precise. Then if to give an extension of trivial representation by itself, you have to give alpha in omega 1, so that d alpha equals 0. Now, and in addition, if you give f in omega 0 with df equals alpha prime minus alpha, then you get an isomorphism between the corresponding extensions. So the category of extension of 1 by 1 is given by just this part of the Durham complex describing cohomology. Now for triple extension, suppose that you have an extension given by 1 cochain alpha, another given by 1 cochain beta. So as I was telling, you should look at alpha beta. If d of alpha beta is equal, and d of alpha beta is equal to 0. If there exists something, the obstruction to existence of an iterated extension is the product of the two classes. So I have this, and I would like to have alpha beta equals d of gamma. Now at the chain level, if you give alpha, beta, and gamma, you define some iterated extension, but you have some freedom in gamma. You can continue the picture like this, and you can have more complicated picture. You can want to have an extension of 1 by 1 plus 1 by 1, for instance. This is given by, in cohomology, we have classes alpha, b, c, and d. The obstruction to have a three-step extension is that AC plus BD is 0 in cohomology, but you also have a train level picture, a co-cycle level picture, when you give representative of those cohomology class, and to give a three-step extension, you have to express the co-cycle you get here as a co-boundary. So you have those two pictures to see that pi 1 unipotent is controlled by cohomology, if you had a slightly more complicated story where you allow some representation, you would need cohomology with coefficients in all sorts of representation and then tensor product as ingredient.
In the simple case of trivial by trivial,
Yes?
if you take that two-term complex omega 0 to omega
Yes.
1 and look at the category of
Yes, it's the same as the category of extension. Yes.
Is there a possible description of that for Sweden?
Um,
Description of that work?
Essentially, I was giving it that, but
That's all indeed so hard.
no, but if one is in Durham, one would tell that one wants to give a connection matrix which will be alpha, beta, gamma. This is the integrability condition for the condition, and you have the notion of gauge transformation.
Maybe it's a two-term complex with something non-abelian. First term, something like that.
I think you really need. What Sullivan would tell is that you either use the differential graded algebra or a minimal model. I would say also for describing the category, the base bond does not occur. It did not play any role here. But if you want to have the Faber functor, the base bond, then the base bond reappear, not for the category. So with this, I've explained why one should expect that for any cohomology theory of abelian variety, one has a corresponding theory of power 1 made unipotent. And I've somewhat told the general machine in terms of cohomology which could give it. Sometimes it's easier directly in each cohomology theory to tell directly what you do to obtain this power 1 made unipotent. So I think that's what I would say in a few cases.
In the first interpretation you gave, that
Yes, with those iterated integrals.
Yeah.
Mm-hmm.
then the relative cohomology of n-fold power of x with
Yes.
respect to these diagonals is,
Mhm.
there is a theorem which says that this is concentrated in degree n only. Hn is the only.
It starts somewhere. Yes, you know that better than.
I think.
That
But
this is related to what one calls the bar construction, starting from the cohomology, and then you have some reduced bar, but.
Well, actually, you don't, I mean, as you once pointed out, you don't need to reduce you have a complex that's cohomology and starts
Mhm.
sort of on diagonal.
Mhm.
My question is, how this stack reflects in the other interpretation.
I don't know.
In the
In-
other
in
one,
the-
by just using cohomologies of x itself. The second.
My view of this goes back to work in 1953 by Frank Adams, maybe even here, because he invented something called the Kobar construction, which was a model for the loop space. And this is just some applying the Durand complex to that.
Yes, yes, this bar construction of what appears here is a kind of description of, that's how Chen think of it also, that one is describing the Durham complex of the loop space. The interpretation in terms of category of local system, I don't know how it fits exactly with, because when one speaks of the loop space, one uses the base bound. Here the base bound does not occur if one wants just to describe the category, but
You can sort of look at it as a relative Durand theory over x cross x, where you
Mhm.
map the two endpoints.
mhm. No, I had some time to fight with those things, but I am not, and cannot pretend I really understand. Now, for the various cohomology theory, one may want to tell more directly what is power 1 made unipotent. So suppose that you have X some algebraic variety over K, then the Durham realization of this power 1 made unipotent is as follows. Here it's the Tannican picture, which is the most convenient. You look at the vector bundle with integrable connection and iterated extension of the trivial vector bundle. Now this is stable by tensor product, perhaps to the dual. So you have some Tannican category, does not yet see the base point. If you give yourself X in Xk, for any such vector bundle you can attach the fiber at X of the vector bundle, so you have an underlying vector space. And now power 1 is given by the Tannican formalism, so essentially defined by the property that to give a vector bundle with connection is the same thing as to give its fiber at X and an action of this group on the fiber, everything unipotent. This is perfectly reasonable definition. In some cases it can be made a little simpler. Now if you, another case which is, yes, then there is, if you take still algebraic over K and a complex embedding of the field into C, then you have the ordinary power 1 of the complex bond, which you made unipotent. And by construction, the category of this group, which is an algebraic group over Q, is the category of local system of Q vector space on this topological space, which are iterated extension of the trivial one. Now, if you extend scalar from K to C and here from Q to C, because of what I was telling of a unipotent completion being insensitive to field extension, you obtain that this, if you extend scalar to C in this ordinary power 1 made unipotent, you obtain the category of local system of complex vector spaces, which are iterated extension of the trivial one. And here, for essentially the same reason, you obtain the category over Xc of algebraic vector bundle with connection, iterated extension of trivial. And now those two categories are equivalent, canonically equivalent by Riemann-Hilbert. And so in this way you get the comparison isomorphism power 1 Durham X, which is an algebraic group over K. You extend scalar from K to C is the same as power 1 Betty X, which is the ordinary power 1 made unipotent, also extending scalar from K to C. So exactly the formalism which you add for cohomology group. You can also consider the L-adic story. There you would take the, not the full profinite power 1, which is well defined, but only its biggest pro L coefficient, and do the same kind of thing that we did. So for going from a nilpotent group to some envelope, and then you will get some algebraic group over QL this time. So we have those direct descriptions.
You know if this also works for singular variety?
I think that's no problem, except you have to define what you mean.
Using the infinitesimal?
Yes, the Yang characteristic 0, of course, to be able to speak of this. Yes, I think there is no problem. I was thinking to it, but in fact, because one should not speak of vector bundle with connection if it is not smooth, but crystals or something like that. This one remained the same. I don't know the state of the literature, but I don't think there is any problem.
So there is an equivalence between local system and crystals even in the singular?
Yes. Oh yes, one thing which make the case I will be at eventually is pi 1 minus 0, 1 in infinity. I should first tell that in this case some nice things happen. That if you have a vector bundle with connection, first, this is the particular case of a variety compactified with a divisor with normal crossing. First, you add those 3 points. In the general case of compactification with a normal crossing, if you have such a vector bundle with connection, it has a canonical extension as a vector bundle along the divisor, with the property that the residues of the connection is nilpotent. So you get a vector bundle the whole of X. And also, this canonical extension is compatible with, it's an exact functor, and so the vector bundle which you obtain will be iterated extension of the trivial bundle if you start with such. Now, on projective line, or any variety where pig 0 is 0, an iterated extension of trivial bundle is trivial. And on a compact variety, a trivial bundle is uniquely trivialized, or constantified. You can look at its global section, and it gives the bundle back. So in that case, one can tell that on such a space, to give a vector bundle with connection is just first to give a vector space. The bundle will be constant bundle given by this vector space. And then you have to give the connection, which will be of the form D plus a one form in endomorphism of V. And the property you need, first it should have logarithmic poles, residue nilpotent, and that's automatic now, the omega equals 0. Because a global one form with logarithmic poles automatically is closed. So this gives a relatively concrete description of the category of vector bundle with connection of the type we consider. So in the case where pig 0 equals 0, which applies here, but I will explain what this description is exactly next time.
Discussion concerning X, smooth or not. What is the, this is, everything is functorial, so if you give from an X which is not smooth to a one degree singularization.
No.
You define
it
the
should.
those connections.
You went of what is it?
You can do crystalline theory instead of the one.
Of course, you have to prove a comparison theorem
Yeah.
in that case. But
Yes, it's probably just comparing H1s.
that is
maybe.
or H1 and H2, and that should
Yeah,
be
H1 and H2.
enough, yes.
That should be enough.
But essentially one has such theory that if you have some possibly singular space and you embed it into something smooth, then you can look at the formal completion in the smooth case of your space, and then the Ham cohomology of this formal space is the ordinary cohomology of the space. You can use that as version of the Ham, so you would look then at vector bundle with connection in such a formal neighborhood, which is formally smooth. That's one way to think of it. And then it should be true that this is equivalent to the crystalline picture.
Right. I see, and I guess it's homotopic to the original space,
Yes.
so the topology
Yeah.
is tidy.
Intuitively, yes, it's a small neighborhood in something smooth. Of course, one has to prove things, but
Right.
I think I did it in 71.
Other question?